The blue bar is the mean aerodynamic chord and the ball is CG. We can drag the ball along z-axis. That will change CG position. Then run the game. As you can see, our UAV is placed on 3 weight scales. Then record the numbers on scale into Excel. I changed CG position, recorded every reading. Using the Excel equation, we can calculate the estimated CG position. In task 2, we will test the thrust. Here is the thrust scale. Run the game, press W, let the UAV move forward until it hit the scale. Open the flight instrument to check the RPM. Here's the RPM reading we need recorded, and here's the scale reading. Input all the data to Excel. In different RPM, the thrust will vary. Then we can plot the diagram. In task 3, we will test the controls. Open the aircraft manager, set the values of input matrix, then we can test the controls in static condition. Now we are going to test controls in dynamic condition. If remove aileron correction in yaw operation, you can see the UAV will also do a roll. In task 4, we make the UAV pitch up and pitch down, and use the data logger to get the angle of attack. We need test multiple times in different CG position, and in different wind speed we can put all these readings into one Excel file. I wrote a Python program to handle the Excel file. We can easily get the result diagrams in different CG position. When CG at a 35% Mach, the performance at different wind speeds are similar, and the absolute values of the minimum and maximum angle of attack are the same. From the wave diagram, we can calculate the period, then we can get the frequency. In task 5, we will test roll rate first. Roll the plane, change wind speed and roll again. Get all the data into Excel, we can get the diagram. It means the higher wind speed, the higher roll rate, and the faster response of the ailerons. Then we test yaw. As the previous operation, we can get the results by Excel. The result shows the short period frequency of yaw is about 4 radian per second, almost half of the pitch. It means the impact of the yaw direction can be recovered more quickly. In task 6, we will test how the CG position on Y affect aircraft. From my test, it can say when CG on minus 0.025, it has 0 thrust pitch. In this part, we will test plane in static wind tunnel by setting alpha and elevator deflections. The test will run automatically. The max value of CL is about 1.25 at AOA 15. This is the drag polar plot. The max value of CL-CD ratio is about 15. When the line crossed the origin, the neutral point is located in same position with CG. It means the static margin is 0. In task 10, we will test high-speed taxiing. We found the UAV seems missing nose gear turning function. The turning is not good on ground, as we seen in flight test last June. In task 11, we will test minimum takeoff speed. Press down after run the game until the plane take off. Read the number in flight instrument when taking off. It's about 17. Accelerate the plane to 21st, then we can trim the elevator by press page up and page down until the plane reach trim condition. We can find 21 RPM that could maintain speed at 20, and the cruise elevator setting is 2.235 degree. Press W until RPM get 100. Try to make the plane steady by press page up and page down. We can find the max trim speed is about 65. By decrease RPM, try to get the minimum speed. From the instrument, we can say the minimum trim speed is 16. In task 15, we only operate aileron, make the plane flat, record angle of attack. From the diagram, we can get the period from 2 peaks. Then, we can calculate the long period frequency is about 10.86. Finally, we will do a circuit flying around the airport. In the first part of flying, I tried to make the plane trim. Adjusting aileron, it make plane little unsteady. Thank you for your watching.